inscribed angle, gentlemen, an inscribed angle is just an angle whose vertex lies on the circle. Pretty simple. Okay? Inscribed angle is an angle that has vertex on the circle. That vertex opens up and touches an arc. It's called their intercepted arc. Let's open it. Oh, there. So the inscribed angle again, inscribed angle is just an angle whose vertex lies on the circle. It's super easy to notice what they are. All inscribed angles, they have to hit some sort of an intercepted arc. So when that vertex, if it's on the circle, if the angle's here, oops, man, this just does not want to move out here. The intercepted arc is what it opens up and runs into. Super visual. Bless you. Very simple to use. Okay. Now, the thing with inscribed angles, the inscribed angle, or else you write, inscribed equals half the arc it hits. The angle equals half the arc that it hits. And you can write this a couple of ways. So if the angle's half the arc, you can say we double the angle, and it equals the arc. So the way we do it. Yes, ma'am? Okay, we can do that during French. This is not French. Okay. You'll have to talk with Madame, or the other guy. Okay, I was guessing. Yeah, just work with her about it, okay? Same idea. You double the angle, and it equals the arc that it hits. What's that? Yeah. Again, the angles, this is super easy to work with, okay? These are super, super simple to work with. Remember last week when we did angles, we had what were called central angles? That vaguely ring a bell? If this angle was 75 degrees, what was the arc? It was 75, right? Now what happens here is that if it's inscribed, it's going to be half that arc. So what's half of 75? You have a calculator. Okay. And that's how this stuff works. It's super easy to work with. Okay? Really simple to work with. Right? For example, oh, we just did that. If I'm looking at this, bless you. What's that? This is decimal. You didn't see that. Sorry. Is that better? Good morning, Joe. It's rough. This first day after a time change, you have to just messes with everything. So this is real tough here. If the angle's 50, what's the arc? Yeah. Remember, you're going out. When you move out, you're doubling. When you move in, take half. Okay. As you go out, you double. You bring it in, you cut it in half. It's very, very simple. Okay. Now, same thing will happen here. Let me move this just a little bit. You said this was 100. What would this equal? 50. Because why? Okay, it's the same arc. Does it matter wherever I put a vertex? As long as it hits that same spot, is it always going to be 50? Yeah. And that's kind of the trick with these things. As long as if they hit the same arc, the angles have to be the same measure. It's really easy to work with.
Oh, I'm so. I'm sorry. did not know. I keep on going. Good. I don't know.
Good morning.
No.
How are you? Same idea. You'll see a lot of this again with the same emphasis where they'll say things that appear to be diameters in fact are. What'll happen now is that we'll be able to figure out angles, we'll be able to figure out arcs, we'll be able to do all the bits and pieces out of each one of these diagrams now. In this case, there's really not an angle, there isn't an angle or an arc we can't solve for. Okay? Angle B, I can say angle B because it's just one vertex on there. That B is 50 degrees, it hits arc AC. What is the measure of arc AC then? 100, okay? So remember, as it moves itself out, that means this has to be 100. What does CB appear to be in that diagram? What does CB appear to be in the diagram? The diameter. So diameters do what to a circle? Cut it in half. So that means what does AB, arc AB, have to equal? Since this is a diameter, this means this has to be 80. Okay? Arc BD is 48. Bring that back down to here. What's that angle have to be? And once again, diameter, isn't it? Back out 48. What do you get? What are you left with? You guys have the calculators. Angles and arcs. This is pretty straightforward. Pretty straightforward. Not terrible? Again, this is, I don't like theorems. I think they're stupid to write out. If you look at angles D and C, why are they congruent? Okay, but why? Yes, thank you, Captain. Notice, if you follow through again, this is where we're going to do a lot of this. See how they hit the same? We were just talking about that? Two angles that hit the same arc are always going to be congruent. Two angles that hit the same arc are always the same. Because they have to be. Okay? They have to be. It doesn't work otherwise. Okay? There's a lot of subtleties that you'll go through with these things as we get into it. When we get to algebra parts of it too, yeah, it's pretty quick as we go through. This section, I think this one's probably the easiest one in circles, to be honest with you. No, I was busy all weekend. Go figure. Basketball games at 8, basketball games at 11:15, Costco runs. I do too. All right, let's do another one like this. Again, we'll be able to figure out everything. You know they stopped doing samples at Costco? Because they were worried about all the sicknesses?
Oh, that's the only reason why I like that.
I know. I heard about it. I'm like, oh, that's. I get it. I totally understand it.
I'm probably going to come back with it.
Okay.
It's okay.
Again, you'll notice here, guys, we're going to have diameters. You have diameters. What are they? Hi. Uh-oh. Just what I always wanted. Thanks. Two newspapers. Don't worry about fight over it once. What does the arc AB have to equal? You're almost there. The arc AB, what does arc AB have to equal? 80, okay. What's arc BD have to equal? How much? What does arc BD have to equal? 70.
35.
What's arc DC have to equal? 110. Arc DC down here has to be 110, because there's your diameter again. Okay? Did you? It's okay, man. I get it. This is easy. This is that diagram again. You probably don't need to draw this one. Notice how angle L and angle M run into the same thing. That means M has to be 52. Double it out and you get 104. Again, don't worry about drawing it. It's not that big of a deal. As you see through these things, I started on my K when I wrote that on there. That was really awful. There's nothing else in one like this until we get into inside angles. When we get to inside angles, then these get a little weird. All right, let's look at a different one. Polygon. We actually did this. We did this one. You can inscribe a polygon if all the vertices lie on the circle. Now, remember when we did the compass, straight edge? Remember how we did the hexagon? You guys that vague ring about? You guys remember making the hexagon? Yeah, it was one of the first days. When we did the hexagon.
Oh, I remember. It was literally the first day of school.
I remember that.
Maybe in the clay.
Good work. When we did this, remember we did the straight edge and we just walked around, we did all the stick marks and all of a sudden it was a hexagon?
Yeah.
Because what we did was a hexagon, we know that all of these marks, well, when we marked, bless you, we knew that all of these guys were the same, which means then all these arcs have to be the same. Okay. We also know now we can figure out the measures of all of those. Do you guys remember how to find the measure of the interior angles? How many sides does a hexagon have? 6.
I said 6, then you looked at me like it was 7.
Good. N minus 2 times 180. How many degrees is that? What's up? What's that one? 720 degrees. There's a total of 720 degrees going on the interior of the polygon. Now, how many degrees does each one or excuse me, how many angles are there in that hexagon? 6 of them, right? So what's 720 divided by 6?
$120, you're welcome.
Thank you. I don't know. Anyway, notice each one of these angles has to be 120 degrees. Okay? This is something we've done. If that angle intercepts that arc, if it's 120 degrees on the circle, how much does that arc have to equal going around it? What do you do to the angle to figure out the arc? Bless you, bless you. Double it. So that means going from here to here is 240, isn't it? Which means going from here to here has to be how many degrees?
The rest of this.
Correct, which is 120. Now, since each one of those segments is congruent, that means that each of those arcs has to be congruent. If these two arcs are the same, and they have to add up to equal 120, what's each arc equal? 60, thank you. So each arc is 60 degrees. And then, do you remember when we drew this one with the compass? We connected all the vertices.
Oh, yeah.
And didn't that make a whole bunch of isosceles triangles?
Mm-hmm.
Or better yet, made equilateral triangles, because if this angle is at the center and it hits an arc that's 60 degrees, that means this is 60. These are all radii, which means these are all 60, and so on and so on. So the hexagon, when we inscribed it, little did you know that everything that we were going to get to eventually was going to show back up.
Oh, no.
So it's just showing that. Remember, the only thing that we're looking at here, guys, is that if a polygon's inscribed, it just means all the vertices touch the edges of the circle. Okay? It's really, really simple to look like. Another one that goes along with that, let me see if I can get the button. So if I have a circle, let's make it a square here. Let's close. What do, stretch this just a bit here. When I have a square inside of a circle, that's inscribed, okay? What are all of my angles? 90 degrees, are we okay with that? Okay. Now, if a square hits this, this is a right angle, which means when it hits the arc, what does this arc have to equal? 180. Now, you missed this part. When angles are on the circle, they equal half the arc they hit. Okay. So now, if that's 180 degrees, that means if I draw it from here to here, it's a what? It's a diameter. Okay. So the idea is, if what's that? What happens here is if you have a right angle, if a right angle is on a circle, the sides, oops, hit the diameter. Okay. The right angle's on the circle, inscribed, if you will. The sides of that angle hit a diameter. Doesn't matter where you put them. It has to. Anytime I have a right angle, this is a right angle, that has to be a diameter. No matter what, it has to be. Okay. Because if you're on the circle, you're half the arc. And every time you double 90, it always equals 180. And every time you have 180 degrees in a circle, you have half a circle, which means you are on a diameter. And it falls back in place. Trying to think of another way to make this answer. There's not really much there. Oh, we just did that. Oh, here we go. This one's kind of boring. So quadrilateral has how many sides? So whenever you have four sides, when you have a quadrilateral, it means your opposite angles, when they're in a circle like this, away. If you have a quadrilateral inscribed, opposite angles will be supplementary. Okay, that's a weird one, because it's not in terms of a, what do you call it? Like a regular polygon or one of those. So what happens here, opposite angles are supplementary. Okay. Whenever you have quadrilateral has four sides, so it works for that one. Your opposite angles have to be supplementary. We all remember what opposite is, right? Just one of it.
Yeah.
Algebraically, then there's just be some sides. I'm trying to think of any other fancy stuff I can throw at you. Like I said, there's not that much with this one, to be honest with you. It's easy. Yeah, we'll call this algebra one here. Oh, that's a 19. Again, if this is going to work, if I wanted to solve for x and I wanted to solve for y, in this case, is that a four-sided figure? Yes. Bless you. Is that four-sided figure inside of a circle? Do the vertices touch the circle? Yes. Therefore, that means each of the opposite angles have to add up to equal how much? 180. Okay. Again, this is super fast. It means these two guys, 17x, 19x, has to be 180, 7y, and 5y is 180. Add them together, 17 and 19, I believe, gives me 36. When I divide that out, what do you get? 5 that gives you 15. Now, the offshoot of this style of problems, they could ask you, what are the angles and what are the arcs? So, when you look at that, there's 4 angles we can figure out, and then there'll be 4 arcs that we can figure out. So if I substitute back in for x, let's see, 17 times 5, 75. So this angle here is 75 degrees. I do that with the 90, that means this one, or excuse me, the 19x, excuse me, that has to be what? Was it 19 times 5? What is it? Oh. What'd I do? Oh, yeah, I did. Hello, good morning. Hi.
70.
Oops. Anyway, so 85, yeah, don't go like, wait, that's not gonna work. So 85 and 95. That makes a lot more sense. Okay? So that means that this arc here, you double 85, what do you get? Yes, thank you. Yes, you get it. Thank you. 170. If I double the 95 going back the other way. Boy, I hope it's going to be whatever 360 minus that was. What do you get, 190? Okay. Do that with the 5y. Multiply that by 15, 5 times 15. There's my 75. And then this one would have been the, we just did 7 times that would be 105. Multiplied by 3 this time. Or added the 3. And again, you can work your way out to get your other arcs, and so on and so on. Like I said, as you get into the algebra of this stuff, it works real quick. There's not too much crazy. Yes, ma'am? What's that? For this one? Remember, because the opposite angles have to be supplementary. So, and I just solved for x and I just threw it out. You missed that little step. But if you found it with the y, you were almost there. Let's see, I think I had this one here. I have the pictures I'm going to look at. Yeah. Let's see if we can draw this one. Oh, that was 84K of this one.